Hello and welcome to the 365 Days of Astronomy Star-Sealer podcast, Questions of a Stellar Nature, with Peter Clark, Hannah Hutchins, and Dr Robert Simpson of the University of Oxford. Hello and welcome.
Hi, thanks.
We're just going to get stuck right in with the questions. So, Hannah?
So what's your favourite area in astrophysics and why?
I ought to say that my favourite area of astrophysics is the one I studied in or schooled in, if you like. So I ought to say it's star formation, but it is and it isn't. I mean, I think for most of us, we fall into these things because we like them. And originally, I was really into astrophysics because of things like Star Trek, and I always thought time travel was cool. And I still do, and I always read papers about wormholes, even though I shouldn't. And so really, star formation is the one I know the most about, and it's a very important and interesting area of astrophysics. But I also love cosmology for answering the really big questions, and I love the kind of really fringe stuff like time travel and wormholes, because it really delves into areas that science fiction only dares touch. And of course, I think like a lot of people, I love planets, so solar system astronomy and astrophysics, and those beautiful pictures of the planets and the moons, and understanding how we all formed and all these landscapes around us, as well as the universe itself. There's probably quite a lot I like about astrophysics, so I should stop rambling and let you ask me the more important questions. But I like a lot about astrophysics, so that would be the short answer.
I'm sure everyone listening will wholeheartedly agree with you. So, moving on to the main topic of our podcast, and that's stars. Recently, the ESO discovered what can only be described as a monster star located within the Tarantula Nebula. R136A1 has been measured to weigh in at a little under 300 solar masses, with an estimated birth mass of 320 solar masses, which is more than twice the accepted mass limit of a star, 150 solar masses. Anything more than 150 solar masses was expected to be unable to reach hydrostatic equilibrium and blow itself apart, as it would be unable to balance its outward radiation pressure with its gravity, and so exceed its Eddington luminosity. Have we discovered something that's a freak event, or are we starting to get below the surface of how high mass stars work?
Well, we certainly haven't really scratched the surface on massive star formation, and this is a big sort of problem area in lots of ways. Well, the problem is that they're not very common, and the reason we thought that the largest stars would be about 150 solar masses was simply based on looking and going out there, looking at big clusters of stars. And this was a paper back in sort of the early, not even 10 years ago, so the early part of the last decade, and basically empirically saying we can't see stars that are bigger than 150 solar masses. So, and in fact, we couldn't see them at the time. It was measured to be 120. Up from there, we thought, well, let's say it's 150 then. It's not the most concrete number. The Eddington limit, which you mentioned, is to do with, so for any given star, it would have an Eddington limit. So that the biggest stars themselves will have very large Eddington limits, but the Eddington limit, or Eddington luminosity, refers to the radiation that would be required to equal the gravitational energy of a star. So a very, very big star will have a very, very big Eddington luminosity, and even the most massive stars we've seen seem to only be approaching sort of a 50% Eddington luminosity, if you like, meaning that the radiation pressure pouring out from those stars is only equal to about half of the gravitational energy. So there's still a way to go in terms of their radiation. So perhaps they could get bigger. This 300 solar mass star certainly does seem to be that big. So what it does is it blows out of the water, as you say, the 150 solar mass limit, but that limit being based on observation anyway. So now we have a new upper limit. There are people that suggest maybe it was, maybe this is a binary system, and we can't resolve them as independent masses. So therefore, you would have two 150 solar mass stars, but that seems unlikely based on measurements of the Doppler shift. If there really were two 150 solar mass stars orbiting each other, we ought to be able to detect that in their spectra. But the measurement is pretty robust, and certainly the technique for making that measurement stands up to the test of other measures of mass that we have. So it really does look like the 150 solar limit is done, and we may be moving on to a 300 for now, until, of course, we find the next one, because theoretically, people have put forward models that suggest we could have anything up to 400, 450 solar masses. So
Wow.
yeah, we could have really big stars, but because the rarer they get, the harder it is to spot them, certainly spot them nearby, which is where we need to see them to measure all this stuff. So it's a tricky business, and hopefully we'll be finding them because the new technology we have, all this infrared data we now have, lets us do a few things we couldn't do before. And one of those is to look at massive star formation in a great new way.
There's a protostar that's been discovered called IRAS 134816124 that is still surrounded by the cloud that it formed from, and it's been confirmed to weigh in at 20 solar masses. And this is particularly interesting as it goes a good way to showing that massive stars form via accretion rather than stellar mergers. Do you now think that we have discovered the secrets to massive star formation, or could a spanner be thrown into the works?
So obviously this relates a lot to the last problem, which is that these very massive stars are hard to come by because there aren't as many of them. And infrared measurements that we have from the very large telescope, the ESO, and a couple of other instruments that are out there at the moment and coming along soon, they all mean that we can look at these things with better detail than we could before. And that's because these things are often embedded within big, dusty nebulae and molecular clouds, and that makes them hard to see with conventional telescopes that we've had up to now. This very, very big one with the accretion disk, as you say, is notable because it's the first time we've been able to say absolutely that this massive star is a very large star. I think it's 20 solar masses, yeah, is that right? Mm-hmm. That it's got an accretion disk around it. Now, the problem was it was thought that with the lower mass stars, it was easy to have accretion. Material can fall onto the star but through gravity and sort of swirl on, and angular momentum gets delivered. But with the really, really big ones, the radiation pressure, the energy pouring out from these new stars ought to be powerful enough to stop things accreting onto the star. So we need to come up with ways to model that and to show that might be possible. And this observation in the near infrared, it's an interferometric observation, meaning it's using more than one dish and putting them together to create an even better picture. This shows that it's definitely possible because it's happening. And this is great for science when things like this happen, because it's always good to just totally challenge the conventional thinking, which had been that perhaps large stars formed by sort of other stars coalescing together. The problem with that, though, anyway, was I don't think I was ever terribly comfortable with that idea. I mean, if you look at the 300 solar mass one we mentioned earlier, how many 100 solar mass stars have we seen around that could have formed to make that one? So it only works for stars that are sort of medium size. Once you get really big, you sort of still need a way to create these things.
So have we now discovered the secrets of high mass star formation?
Oh, no, absolutely not. Well, I don't think we've discovered the secrets of massive star formation at all. I think what's great is to uncover a new piece of evidence that gives us a new line of inquiry. So, okay, so massive stars clearly can form through accretion. Let's figure out how that works. And is that how they all form? Don't know, but certainly how some of them form, because we can see one. So yeah, spanner in the works, definitely. More spanners in the works? Why not? That's kind of what science is about, right?
Thank you for listening to the 365 Days of Astronomy Star Stealer podcast, Questions of a Stellar Nature, with Peter Clark, Hannah Hutchins, and Dr. Robert Simpson of Oxford University. Thank you.